we're going to talk about instantaneous velocity, which has this formula. So if you know this equation, you can move on to the next video. Sometimes average velocity, which you learned in the last videos, is the only thing you care about. For example, in a bike race, the bikers have to travel a certain distance, and the person with the shortest time is going to have the largest average velocity. You don't care if they go fast at the beginning and slow at the end, or slow at the beginning and fast at the end. It just matters about their average velocity. Let's take a look at the train example again. Just like in the last videos, we're going to treat this as a point, and we're going to start it at x equals 0 just to make things simple. Let's say it has the following motion. The shape of this curve might look familiar. This is actually a parabola. And the train's displacement can be given by this equation, x equals t squared. There's an extra factor there, 1 meter over second squared, just so that the units work out properly. Also, if you like, you can add a t in front of the x to emphasize that x depends on t. So a quick example, if we want to know where the train is at 1 second, we just plug in 1 and we get to 1 meters. If we want to know where it is at time equals 2 seconds, just plug in 2 and you get 4 meters. In a previous video, we looked at the average velocity between 2 points, let's say A and B, which was given by this equation. In this case, we can actually calculate the average velocity between t equals 1 and t equals 3, since we have the equation for x. And we get to an answer of 4 meters per second. Now let's say we wanted to know the velocity exactly at point A, so that instant in time when the train is at point A. Clearly the average velocity that I just calculated isn't going to give me the velocity at A. I can get closer to the instantaneous velocity by taking a shorter time step. If I take my delta t to be 1 second, then I get to an answer of 3 meters per second. I'm going to make it smaller again, and again, and again. And I can continue like this, making the time interval smaller and smaller. It'll keep getting closer to 2 meters per second. In other words, 2 meters per second is the limit that we are approaching. It seems reasonable to say that the velocity at point A is 2 meters per second. Instantaneous velocity is delta x over delta t in the limit where delta t is getting smaller and smaller and approaching 0. I'm writing 3 lines here instead of an equal sign because I'm defining the quantity Vx. You might recognize the quantity on the right hand side. It has a special symbol. It's called the derivative, and it can be written dx over dt.
Yeah! Yes!
Personally, I've never liked this notation, since to me it looks like a fraction, but it's not a fraction. It's the derivative of x with respect to t. You might remember from calculus that the derivative is the slope of the curve. So the instantaneous velocity at point A is just the slope of the curve at point A. Thanks to calculus, we can get the answer for the instantaneous velocity very quickly, without having to go through the steps of taking delta t to be smaller and smaller like we just did. If you know how x depends on t, then you can just plug it into our equation and differentiate. First, I'm going to pull out the factor of 1 meter over second squared, since that's a constant, so it can always be pulled out of a derivative. Then I differentiate t squared, it becomes 2t, and we have the equation for the instantaneous velocity. Again, if you want, you can write Vx explicitly as a function of t to show that it depends on t. It's up to you. Now if we plug in t equals 1 second, we get our answer, which is 2 meters per second.